So today we're going to talk about the atomic structure again in terms of understanding how the electrons work, but how the nature of light helps us understand that. So the first thing we want to make sure is we understand what the nature of light is. And of course, so we start with the wave nature of light. And so to begin, let's talk about light in terms of being emitted or absorbed. And so when light is emitted or absorbed by substances, it turns out it gives us clues to the atomic structure of the atom. And when we look at the visible light, what we can see, it turns out it is part of what is called the greater electromagnetic spectrum of radiation. And when we analyze visible light as well as other types of electromagnetic spectrum, we get an idea as to how it's formed, and in turn helps us understand the structure of the atom. And so let's start with where it is in the electromagnetic spectrum. So in the electromagnetic spectrum, we start with radio waves. It is the lowest energy out of all of them. Then we have microwaves, we have infrared, then we have what we can see, which is the visible light. We have ultraviolet, which is just beyond that, soft X-rays, hard X-rays, and gamma rays. And so gamma rays are the most energetic. And today in class we talked a little bit about wavelength and frequency. And when you look at wavelength, it turns out that as you move to the right, you can see how the numbers get smaller and smaller. You can see it's 10 to the negative 12 over here in terms of meters, and 10 to the 3 meters, 1,000 meters long for radio waves. On the other hand, when we talk about frequency, you can see how the frequency over here is 10 to the 6, and when we get all the way over here, it's 10 to the 20. So as it turns out, we get shorter wavelength on the right-hand side and longer wavelength on the left-hand side. So radio waves have long wavelengths, X-rays and gamma rays have short wavelengths. And in terms of frequency, the lower the frequency, radio waves would have low frequencies, gamma rays and X-rays have high frequencies. And when we look at this, you say, okay, so what's the relationship between this and energy? Well, we talked about in class how these are the most energetic on the right-hand side. And so anything that's highly energetic typically has short wavelengths and high frequencies. Whereas we talk about things that have low energy, like radio waves, have very long wavelengths and low frequencies. And so they're kind of reversed, and again, that's all related to the formula we'll talk about here in a second. So one other thing I want to talk about in terms of the visible light is that there's even an energy within the visible light that I want to talk about. And to help us understand that, you learn, of course, Roy G. Biv, right? Roy G. Biv. And Roy G. Biv basically tells us the sequence of the energy as well, as just like in the rainbow. Red, which is right beside infrared, is the lowest energy of all the colors. Violet, which is right beside the ultraviolet, is the highest energy of all the colors. So as you go from left to right, you're talking about violet having the most energy out of all the colors, and red having the lowest energy out of all the colors. So that's another piece of information you want to make sure you remember. So when we talk about properties of waves, we want to talk about, of course, is wavelength. And wavelength is just by definition the distance between identical points of successive waves. So you have waves, of course, that go in a pattern, and the idea is, which one of these guys, how do we determine the wavelength? Well, as long as we talk about the same points, where I talk about a crest to a crest, or a trough to a trough, you can measure those and actually determine the wavelength. And you can see these two different waves that are over here. This is the bottom half of it, that's the top half. Whereas over here, we're talking about something with a shorter wavelength. And based on what we talked about, shorter wavelength means that you have higher energy for this type of wave. So the shorter the wavelength, the higher the energy. The longer the wavelength, the lower the energy. The other thing, of course, we can talk about is the amplitude. And of course, as I said in class, this is not the most important thing for waves. So for the most part, I'm going to skip this, but you can see from the drawing that it's just the height of the wave or how tall it is. And of course, you've seen that in waves in the ocean, so it's something that you are familiar with, I hope. In terms of properties of wave, of course, the wavelength is the length between them, but one other important property we talked about in class today was the frequency. And frequency is the number of waves that pass through a particular point in 1 second. And by definition, it is a cycle per second. And so if a wave is passing by, the frequency would then be determined by how many cycles pass by per second. As you saw the demo in today's class, as I generated a frequency off the spring, the higher the frequency I generated, the more energy I had to put in. And so this frequency concept is that you need to make sure you understand that the higher the frequency, the more energy you're putting into the wave. And you know, when we talk about what electromagnetic spectrum, electromagnetic radiation looks like, it turns out there are two perpendicular components to it. There's a magnetic component, the magnetic field component portion, and the electric field component. And for the most part, that's a physics topic, so we won't cover that in this class, but it's just good to kind of know that there's a perpendicularity to it, and that's why you can have polarizing films for your sunglasses and things like that. So for the most part, just know that electromagnetic radiation is the emission and transmission of energy in the form of electromagnetic waves. Okay? So an important idea, of course, that we then moved on in class today is that the speed of light, in terms of how electromagnetic waves travel, all of them on that spectrum we talked about earlier travel at the speed of light. Whether it's a radio wave, whether it's a gamma radiation or visible light, they all travel at about 3.00 times 10 to the 8 meters per second in a vacuum. And of course, for air, because it slows down a little bit, it's pretty much the same speed. And we use that to then calculate the relationship between wavelength and frequency. And so the formula C is equal to lambda times nu, or wavelength times frequency, becomes a formula in which we can then calculate the wavelength or the frequency. And of course, you saw from our table that the frequency and wavelength are inversely related. And you can see that since they're both equal to a constant when you multiply them, that if I increase the wavelength, then the frequency has to go down. And if I decrease the wavelength, then the frequency has to go up when we're talking about electromagnetic radiation. That's not necessarily the case for all sound waves and other kinds of other waves. It all depends on what the medium they're traveling through. So in terms of electromagnetic radiation, just know that all of them travel at the speed of light. Okay, so that's an important concept to remember. All types have wave characteristics. They have wavelength, they have frequency, they have amplitude. Because all EM radiation move at the same speed, the wavelength and frequency, we say, are inversely proportional. So again, there's that formula right there, C equals lambda times frequency. And keep in mind, you need to make sure that if your wavelength is not in meters, that you convert it to meters. Most of the time you'll see it in nanometers. So nanometers you're going to have to convert to meters. And of course frequency will typically be in hertz, so you won't have to actually calculate or convert those. And again, as I said, the wavelength, as it will go down, you can see it getting shorter and shorter. And you can see that the frequency increases. There's an inverse relationship to that. And that's a very important concept when we talk about the relationship between frequency and wavelength. So this is in opposite directions. I don't like showing this slide, so I'm just going to move past this one because it doesn't help me with my Roy G. Biv colors. You can see down here it's like Vib G Yar or something. I can't even do that. So Roy G. Biv is easier. So in terms of a practice example, why don't you pause and try this one if you want to try it. So you have a photon has a frequency of 6.0 times 10 to the 4 hertz. Convert this to wavelength in nanometers. Does this frequency fall in the visible region? So when we do this problem, of course we use the same formula. And you plug it in. To solve for lambda, I have to divide both sides by frequency. That's why you see that work done right there. We plug in the numbers, 3.0 times 10 to the 8th meters per second divided by 6.0 times 10 to the 4 hertz. And as long as you're in hertz, and as long as you're in meters per second, your units will be meters when you're done. And so you get 5.0 times 10 to the 3rd meters. And so when you look at which one does this fall into, you have to go back a few slides. And going back a few slides, let me go back. You can see 10 to the 3rd is right here. It's a radio wave. And so 10 to the 3rd wavelength, when you plug that in, turns out to be 10 to 12 nanometers. It is a radio wave. Okay, so it is a radio wave. So from here I'll just pause and then we'll move on to this in the next lesson. I'll talk about quantized energy and photons.